All right, so today we're doing recommendation engines. Um, this is mainly going to be a slide deck, mainly because a lot of recommendation engines can be built with the algorithms that we've learned last mod and earlier this mod. So when those parts come up, I'll just talk about how you can do that. And then here, I just have a notebook that has the implementation of the main recommendation system algorithm that we're going to use that we didn't use before. So yeah, that's going to be the structure. Today, we're going to talk about different kinds of rec engines. There are three main types. Again, we'll get into it later. We're going to talk about the concepts behind each kind of engine and also pros and cons when to use which. So there are three main types of recommendation engines. The first is non-personalized, which we'll start off with because that sounds the most simple. Later, we'll see that there are also content-based recommendation engines and collaborative filtering recommendation engines. When we get to it, you'll see that most recommendation engines will fall in either content-based or collaborative filtering or hybrids of both. And it is going to be dependent on what kind of data you have, which one you would build. So we'll talk about those later. So why do we need recommendation engines and what are some examples? We need recommendation engines to push products, to decide what we consume. And examples, I know you have like Netflix that makes recommendations. Spotify has like their playlists. My favorite recommendation engine is actually the Facebook advertisements that I get. I think that they're like hyper specific on what I'm eating at the time. So yeah, that is also a recommendation engine. Just to start off easy, non-personalized recommendation engines. Let me just make sure everything is up on the page. There we go. So non-personalized recommendation engines, as the name suggests, everyone will just get the same recommendations. For example, top rated items. If people have been rating a bunch of things really highly, you can just push the highest rated product because you can assume that if it's highly rated, more people will like it. You can also do the most watched consume items, same principle as recommending top rated items, but also you could recommend items that will give the company the highest ROI, and ROI stands for return on investment. Well, a really quick pro of non-personalized recommendations is it's easy to make recommendations because everyone just gets the same thing. You could code something in Python to always return the same output in a recommendation engine. However, is it the most effective? Arguable both ways. You can see that this is just an example of like a YouTube page with nothing signed in. You can see, well, it's kind of small, but you'll see here that they just recommended the top trending videos at the time, which makes sense. Some scenarios in which you want to use non-personalized rec engines, very likely in your projects, you won't just be doing a non-personalized engine because there's no model behind it. But just imagine a scenario of your new business with not too much data on content and not many users to get data on. When you really want to push certain items, this kind of recommendation engine makes sense. Also, this kind of recommendation engine could be something that kickstarts your data collection process, right? As you know, imagine you're a new business selling goods. As people buy things that you recommend or push out, you eventually get reviews, and it's just a form of data collection. So non-personalized recommendation is really straightforward. We won't probably will not code it, but later I'll talk about a scenario where you might. Questions about this?
So let's say there are some companies who say that, okay, we want within our website, right, some recommendation things to be implemented. So do we code that within the website codes, or like it's like we will code it separately on a dashboard and then add it to their website?
That is really dependent on how the website structure is set up. So if the website, in some websites, if it's very simple, I know you can just put the URL of the item that you want to push out on the web page itself. But yeah, if it's from a dashboard, you can also, filter it to only give out like certain things, and that same principle. Yeah.
Okay.
But the point is that there's no model here. There's no model at all.
Okay.
All right. Anything else?
So it's just a ranking. When you say no model, it's just like a ranking, like
yeah,
the top
it's pretty
number.
much. Yeah, it doesn't even have to be a ranking. It can literally be like you're telling everyone that this is what I want to recommend right now.
Right. But you say like the trending one, these are the most, like you sort all, and maybe even like if it was a Pandas database, you could just be like, this was for this hour, these have the most views. So I'm going to sort them by these most views and show, the top 10 of those sorted.
Yeah,
like
absolutely. Yeah, that's definitely a way to do it. But yeah, the fact is you can code Python functions to return these like top rated items. But yeah, there is no machine learning happening here.
Okay.
All right, let's move on to content-based recommendation engines. So content-based recommendation engines makes recommendations based on an item's features. So if you have a data frame that looks like this is just an example of like a movie data frame. So every row is a movie, every column is a different aspect of the movie. So you can see here we have genre, actor, director, year, IMDb rating, maybe a Rotten Tomatoes score. And models that we already know can actually do content-based recommendation engines. So for example, what you can do is you can cluster all your movies based on all their features. And so you know that if somebody likes a certain movie, you can recommend other movies within that cluster. Also, if you happen to have a lot of information on a single user, so let's say I watch like a Netflix movie every single day for the past year, I would have like 300 movies. I maybe will rate them thumbs up or thumbs down. That can be my label, and you can build a classification algorithm off of this kind of data. So imagine if I watched a movie every day last year, and then like I have all of this data for all the movies, and as my target, I have like ones or zeros, just saying whether I liked it or not. You can build a classification algorithm per user as a recommendation engine. Finally, and the simplest way to go about a recommendation engine is through nearest neighbors. And so I think I alluded to it when we talked about KNN, but within nearest neighbors is a whole group of algorithms, not just k-nearest neighbors as a classification algorithm. So k-nearest neighbors just relies on distance metrics. So let's say I really like movie 3. A recommendation that makes sense would be the movie that is just closest to movie 3, or like the next 5 closest movies to movie 3. Again, that is assuming that you turn all of this information into numerical data, and then you can feed it into a nearest neighbors model. Any questions about this?
Yeah. What happens when we are creating different clusters with k-near? So let's say if there is a cluster based on KNN, and that cluster is saying it's only based on genre.
Yeah.
Right. So in that case, we can recommend based on genre. We mention that, okay, this is based on genre. This is what we recommend, or based on what you have searched in the past, something.
Yeah, absolutely. Based on, if you're using some sort of distance metric, you can definitely pick out the reason for the recommendation. Like, for example, let's say movie 1 I really, really like, but I don't know about all these other movies. Basically, if let's say movie 2 is the most similar to movie 1, I can just inspect the magnitude of the difference between each value in each column. And the one with the smallest magnitude is likely the most salient reason why it was the most similar. So for example, let's say that these are both horror movies. Then that means, again, you would do like a get dummies and you have a horror column. Out of genre, your horror column would be a 1 here and a 1 here. Difference would be 0. The distance in that column will be 0. You will have differences in all the other columns, but if you're trying to figure out the reason for the recommendation, it would likely be the ones where the difference is 0. So if any values are the same across both rows, and that is something that you can extract pretty easily. Once you have your base movie, you pick the nearest neighbors, all you have to do is look for the minimum difference across all the columns. It might be multiple columns as well. It could be due to genre, maybe they came out in the same year, maybe same director. But yeah, you'll get that information if you inspect your result of your nearest neighbors.
Would you be able to do something like Scorsese is, a 40 and Coppola is a 45, but they're a lot closer than, say, I don't know, some schlock director that doesn't get Academy Awards. Like, could you do that too and like quantify? Is that how you would do it with like directors?
So the easiest way to go about it would just make a single column for every director, right? What you're saying is actually alluding to something that we'll talk about later in neural networks. So basically later what we can actually do is every director can have like a numerical representation. What the numbers mean, the numbers don't mean anything, but it basically can measure, you can basically measure distances between entities. And a lot of these like vectors already exist. So for example, I'm sure like big names like Coppola or what was the other one that you mentioned? Scorsese. Yeah, I'm pretty sure, well, I'm not going to confirm, but there are a lot of like these named figures that have vectors associated with them. And we actually will talk about those a little bit when we get to NLP, just because that is where those come from. But basically that is trained on like on context surrounding these people. If that doesn't make sense right now, don't worry. But yes, what you're saying in like quantifying different people or quantifying, actually, yeah, different people like directors or actors, that can definitely be done.
Okay.
And then you can just build the model the same way.
And you can also maybe say like horror is numerically close to suspense, but it's farther away from rom-com, like that.
Yeah, that can be done too. Yeah, so far we've only talked about dummy variables. This whole idea of transforming like genres into numbers that have context embedded, these are called word embeddings, and we'll get to those in NLP and a little bit in neural networks. But
so,
yeah.
One quick question. Now, what happens if we have, let's say, multiple target variables?
What do you mean?
So let's say now if one of my target variable is based on the price selection of somebody. Let's say I want to watch a movie which is from either from Netflix or from Amazon Prime, but like Amazon Prime is charging me $10 per month, but Netflix is charging me like $9 per month. So one of my target variable can be this. Second target variable can be like, okay, based on the genre, right? If they say what genre movies Amazon has or what genre movie, Netflix has.
Yeah.
So if I have multiple variables, is there a formula then like where we say that now, as far as I could understand that I had to specifically have one variable as a target and then go ahead focusing on that variable and go ahead.
Yeah,
right?
For sure.
In recommendation, do we have something?
No, yeah, for sure. I mean, it's actually not even like, okay, so let's say I know that I want to watch a comedy movie. I don't care what movie it is. I just want to watch a comedy and I want a comedy recommendation. Or like, let's say I only want to watch a movie that exists on this platform. Those are actually just filtering out your data frame before you run any model. So you would just literally like filter out, I only want to watch something that's available on Hulu, or filter out, basically, I don't want to watch, let's say I only want to watch a comedy movie, I will just filter out the comedy movies and then run the nearest neighbors on that. Just because nearest neighbors, if you all remember, you're computing distance between one thing and everything else. If you can reduce the number of things you have to compute distances for, even more efficient.
So in the same Jupyter notebook, if we run multiple target variable, let's say when we are creating multiple models, each model, if we have different target variable, and specifically, let's say if we have here in the movie data itself, like if we have multiple data, will the model change if we change the variables?
It depends. You can set it up such that you're retraining a model with a subset of variables, or you can keep the same model and then just have like, 0 values for the variable that you don't care about, or the 0 values for the variable that you've already subsetted. But yeah, the main point of this presentation is more about the other kind of recommendation engine, so I don't want to spend too much time on this. For this project, for Mod 4 project, if you want to do a recommendation engine, it will not be this kind of recommendation, just because these algorithms we've already dealt with, and the focus of this presentation is going to be the next kind. But I still want to talk about this too.
Okay.
But just for context. Anything else before we move on? All right. So really quickly, I talked about similarity metrics. These are just a bunch of similarity metrics. Some of them should sound familiar. For example, Euclidean distance. Euclidean distance is just like, your Pythagoras theorem. Jaccard index is a new one. It's basically weighing how many of your features are the same versus how many are different between each data point. Cosine similarities we've talked about is just the angle between vectors. And Pearson correlation, actually I believe I have a slide later that actually says that Pearson correlation experimentally, which means that like in recommendation systems that exist in the world, work best with Pearson correlation as the similarity metric. So that's just a fact that's good to know. So content-based recommendation engines, if you're thinking about doing this, what are some pros and cons? As like a quick anecdote, I bought one plant one time off of Amazon. I killed it, but for like weeks, these were my recommendations. You get very, very specific. If I have very specific tastes, you get very, very specific content. As a con, you can imagine that, all right, if I've only ever liked horror movies on Netflix, my recommendations will only be horror movies. If you just think about it from a content perspective. I mean, this could be a good thing as well, but again, it really depends on your context. One pro of content-based recommendations is there is no cold start problem. The cold start problem is something that we're going to talk about in the next batch of slides, but basically, in short, if you are a new user, it becomes easier to generate recommendations for new users versus collaborative filtering recommendations, which we'll talk about later, and I'll call back to this as well. Questions or thoughts about this?
You said cold start, correct?
Yes, cold start. I'll talk about it later too. All right, so this is what the bulk of the presentation is about. It's about collaborative filtering. And collaborative filtering is a whole genre of recommendation engines that have to do with users and items. So previously, we were just dealing with items, therefore it's content-based. Let me see, content-based recommendation engines, because you're making recommendations purely based on what the item is. But in collaborative filtering, you're actually going to make use of multiple users' ratings on items. Yeah. So before we get into it, a cornerstone? Yeah, a cornerstone of collaborative filtering algorithms is the utility matrix, and this is what our data is. So utility matrix shows different user ratings of different items. So this is an example. Let me see if I can. I don't know how much bigger I can get this, but basically what this is every column is a movie, every row is a user. And obviously, not every user would have seen every movie. Therefore, you have a lot of blanks. So for example, in this case, user 1 rated movie 1 a 1 and movie n a 3. User 6 rated movie 1 a 4, movie, whatever this is, a 5. And so with a data set that has this kind of information, you can build a collaborative filtering model. The idea here is to fill in these blanks and then recommend the items with the highest prediction. So for example, this is just an example of it filled out. For user 1, out of all of these movies, I guess 4 is the next highest thing. So you would recommend movie 2 to user 1 as a result. Any questions on the setup of the utility matrix? I will say it usually doesn't come in this form. It usually doesn't come as like a users and then movies in this matrix form, just because it's pretty inefficient. You imagine all of these will be like null values or zeros, which is not what we want. So usually it comes in the form of, all right, user 1, movie 1, all right, this is going to be a 1. User 2, movie 2, 5. So this is known as a sparse matrix, and usually it comes in like, instead of this like n by m matrix, it usually comes as like a 3-column data frame with user ID, movie ID, rating amount, so that it doesn't, it doesn't take up as much space. And we'll actually see an example of that in the code later. One more thing, it also doesn't matter if like items are on the rows or columns or users are on the rows or columns. It can be flipped and you achieve the exact same thing. All right. So collaborative filtering basically recommends items based on the ratings of other users. The whole idea here is, if let's say I like, I don't know, The Avengers. If I like the movie The Avengers, and then I know that you also like the movie Avengers, it makes sense for you to ask me for my movie recommendations because we have similar tastes. So going off that principle, that's how recommendations are being made in any collaborative filtering model. There are different ways to do collaborative filtering. There are memory-based methods and model-based methods. I will say that memory-based methods, these are more used for baseline models. And then this model-based matrix factorization method is the like formal model that we're going to talk about today. So we will talk about these memory-based methods as well, but they're mainly used for like a baseline or a really, really quick formulaic way to generate recommendations. Questions before we get into some math stuff? All right. To start,
maybe we'll go over this.
Oh, yeah.
What does the term matrix factorization mean? Will you discuss that in more detail?
Yeah, we're going to talk about it later, but basically you're going to express one matrix as a product of multiple matrices. And we'll talk about that later.
Okay.
Yeah. All right, so one thing to just remember before I get into this, we're going to start with 2 memory-based methods, but these are not used very commonly, just good to know as a baseline. But then we'll build on to matrix factorization. So to start, we have user-to-user collaborative filtering. And this process is just filling up the utility matrix based on user similarities. So this is just a quick example of a utility matrix. These are just random values. And for simplicity's sake, let's just try and find out what this predicted rating is. So here you have 4 users, 4 items. We just want to try and fill in this question mark. We want to know, what did user 1 rate item 3? So the process of this, really just 2 steps. First, you're going to compute user similarity values. So how similar is user 1 to every other user? So here I'm using cosine similarity here. And these are just the similarity values between the users. So between user 1 and user 2, it has a 0.65 similarity. And between user 1 and user 3, 0.76. Between user 1 and user 4, 0.83. These similarity values, I believe, are are generated by just these 3 items values, if that makes sense. Because this is a blank, you can't really compute similarity here. We're just comparing the simile of 433 to 222, and so on. And so that's where this comes from. So now that we have these similarity values, the next step is to just take the weighted average of the others' ratings. So you can see here in this equation, I'm basically taking the weighted average of the other users' ratings for item 3. So you can see here 454 is what the other users rated this item. And here I'm multiplying the similarity by 4, 5, and 4. And then I'm dividing it by 2.24, and 2.24 is just the sum of all the similarity values. And then you end up with a predicted rating of 4.34. Any questions?
Okay, can you explain the math again? Because you're taking the weighted average. And
so you can see here, it's 0.65 is the similarity between user 1 and user 2. So we're going to take 0.65 multiplied by user 2's rating of this item. And then here we have 0.76 for user 1 and user 3. So we're going to take 5 from user 3, which is here, 0.76 times 5. And then same here, 0.83 for user 4. So we're going to multiply 0.83 times 4, divided by the sum of all of these 3 to get 4.34.
Okay.
Anything else to clarify? Cool. All right, so this is it. This is user-to-user collaborative filtering. Really quickly, before we get into more collaborative filtering, let's talk about some pros and cons, because the pros and cons are the same for all the next couple of algorithms we'll talk about. So the pro, obviously, is personalized per user. Some cons is that one is kind of computationally heavy. In this example, we only have 4 users and 4 items. But as you have more items in your catalog and more users on your platform, the computation power that it takes to calculate this blows up. There's also popularity bias. So popularity bias, imagine like these, for item 3, everyone really liked item 3. And so instead of a 4, imagine that these were both 5s. No matter what your similarity is, your predicted rating would end up being a 5 if every other user has rated it a 5. So that's a popularity bias. Usually, like if you think about all the times you had an unpopular opinion, this would not pick that up. And finally, the cold start problem. So the cold start problem, imagine if user 1 didn't have any existing ratings. If user 1 had nothing here, we would have nothing to compute the similarity values to start off. And so cold start problem is a huge deterrent to using collaborative filtering models. So usually you would use a different model to try and generate ratings in your system, then you can move on to collaborative filtering. Questions so far? All right. Well, the next one is very, very similar to the last algorithm that we talked about. It's item-to-item collaborative filtering. Same algorithm, just done on a different axis. So here we're going to fill up the utility matrix based on item similarity. So previously, we computed the similarity between users. Now we're just going to do the same thing for each item. So we're just going to see how similar is item 3 to all the other items. So here we've gotten 0.78, 0.83, and 0.87 for items 1, 2, and 4. And then it's the same process. You're taking the weighted average again. But instead of 4, 5, 4 here, we're doing 4, 3, and 3 for user 1. And then you end up with a predicted rating of 3.31. So same process, but we end up with a different number. The previous number that we got was 4.34. This time you have 3.31. So this is going to set up our final model. But here you can see that you have a difference of about like 1 whole star in rating just by looking across a different dimension of your data. Questions about this? All right, the algorithm itself is pretty straightforward. There's no machine learning here. It's not gradient descent or anything. It's just computing similarity. All right, so we've talked about user to user and item to item, which is better. In general, item to item has just proven to be more effective. Again, this is only through recommendation systems that have been deployed and have data generated, just because it's harder to predict users' unique tastes. So one other thing to consider is your complexity. So if you have m users and n items, these will be the complexities. Basically, because for m users, if we're doing user to user, you're going to first have to compute the similarity between each user and every other user. So there is more work done on the user's front, and then items, it would be the same for items. So which would be faster if you had more users than items? So imagine if m was greater than n, which one of these would end up being bigger or smaller, sorry. Item to item would be faster because you have to do less computation overall if you have fewer items. And as I mentioned earlier, experimentally, Pearson correlation has demonstrated to be the best similarity metric here. So I did use cosine similarity, but experimentally, it just says that if I were to use Pearson correlation instead, my results experimentally would be more accurate. Questions about this? All right. So we're going to move on to talk about the final algorithm, which is going to be the main algorithm that you're going to be using, especially for those of you who want to do a mod 4 project on recommendation system. So this is the model-based collaborative filtering, if you remember. So
one quick question. So now the recommendation system cannot be merged with the other, for example, a time series based model or.
I would say directly no. But if you find a way to tweak it such that either you can get some content information or you can kind of like proxy ratings for something else, then yes, but directly no. Just because they're very different models. Like this next one we're going to talk about is a matrix method. Time series models, we're actually going to start talking about time series on Thursday. Time series is a linear model.
Okay.
All right. So model-based collaborative filtering. Singular value decomposition, which might sound familiar because we actually talked about it during PCA. So SVD, singular value decomposition, is the way that PCA was done. This is kind of another way to fill in the utility matrix. So SVD is a form of matrix factorization. And as Henry asked earlier, matrix factorization is just the process of expressing a single matrix as a product of multiple matrices. Typically, SVD breaks down into 3 different matrices. If you remember the terms like eigenvectors and eigenvalues, that's PCA stuff. This collaborative filtering model uses a modified form of SVD, so no eigenvectors, no eigenvalues involved. The idea here is to break down the utility matrix into a user matrix and an item matrix. I do have diagrams later to show how this works. Other dimensions are latent features. Again, I'll show you that later. And this process actually does use gradient descent. The gradient descent process has a specific name. It's called alternating least squares, and we'll sort of see why that is later. And something that's good about this model is it does preserve the relationship between items and between users. We'll take a look at that and how it works later as well. It's very, very heavy math, but the best-in-class models use some form of SVD. The story I like to tell is back in I think 2007, Netflix used to hold this competition every year where they just release a bunch of user ratings as a train set, and basically people will have to build algorithms to try and predict movie ratings of, of other movies. And basically the person who came up with SVD4 recommendation systems, he won the competition predicting Netflix ratings of movies to like a 96% accuracy, which you can imagine, like, everyone has very specific tastes. You have so many users and so much content on Netflix. Getting a 96% accuracy on Netflix rating is pretty impressive. So let's get into the algorithm. So as I mentioned, we're factorizing this matrix. And factorizing, again, is just expressing the utility matrix here as a product of two separate matrices. For our purposes, we're gonna factorize it into a item matrix and a user matrix. If you remember matrix multiplication, which it's fine if you don't, if you remember matrix multiplication, this is the same utility matrix from before. If we want to fill in this square over here, this square, if you were to multiply this back up, is determined by item 3 and user 1. Then this like 2 columns and these 2 rows over here, these are latent features. What latent features here means, it just means that these 2 x's are just some numbers that just represent the item. The numbers themselves don't have any inherent meaning, but basically you can express item 3 as 2 numbers and user 1 as 2 numbers. Again, it's just some representation of the user or the item. The number itself has no meaning. Question.
And why 2 numbers?
Oh, so that is actually a hyperparameter that you get to tune. Basically, the more numbers, the more granular you get when like describing the item or the user. 2 numbers in this case, just because it's easy to show. But yeah, you get to tune that in your model, and I'll show you all later. One thing that you tune is how many latent features you have. The more latent features you have, the more complex your model will get, the slower it will run as well.
And you're saying latent features are just an arbitrary number that you're assigning to these items or users?
Yep, that's right.
So I3 could be 4 and 7, and UI could be 9.6 and whatever, 8.7.
Yeah,
okay,
exactly.
Get into more.
Just whatever these numbers are, these numbers, and if in matrix multiplication, basically the sum of this times this plus this times this will give you this.
So they are totally arbitrary. They will end up ending up, somewhere between what, 2 and 5.
Yeah, very, very likely. But yeah, but the numbers themselves, like the individual numbers that appear here, will have no inherent meaning.
Right.
Yeah. Okay. Not to throw another wrench, but the process gets a little more complicated from here. We're going to do gradient descent. So gradient descent, you can imagine we want to fill in this number over here, but you can't really do matrix operations when you have a missing value in your matrix. That's just not possible. And so we're going to reverse that. Instead of trying to just fill in this number, we're going to try and recreate this matrix to match this matrix as much as possible. So I'll just say that again. We're trying to recreate the utility matrix to match our original utility matrix as much as possible. And we do that through a process called alternating least squares. So as you remember, with gradient descent, you always start with some initial values. And where you initialize values, you're actually going to initialize them here in the I'm going to call these the component matrices, but this is basically the same thing, just backwards. This is the item matrix, user matrix, same item matrix, user matrix, and we're just going to initialize all these values to be 1s to start. It doesn't always initialize as 1s, but this is just an easy example to show. Initializing these 2 as 1s, if you do the matrix multiplication, it actually creates this matrix of all 2s. Again, it's just matrix multiplication. If you need to revise, that's in linear algebra. So right now we've tried to recreate this utility matrix of all 2s. What you can use to determine how similar this is to the original matrix is RMSE. And RMSE we're all familiar with. This RMSE is just calculated by taking like the element-wise difference. So here you can see like user 1 item 1 2, user 1 item 1 here is 4. It's just the root mean squared error of all of these differences. So 2 here, 4 here, 2 here, 2 here, 2 here, 3 here, 2 here, and 5 here, and for the entire matrix. So basically this RMSE value of 1.75 is the average difference in each element across the 2 matrices. Questions about this? Okay. So from here, what we're going to do in our gradient descent process is we're going to keep changing values in our component matrices that will eventually change our recreation matrix to match this better and better. So let's just do one round of gradient descent, and the same process. You basically do the same process over and over. So to start, let's just try and optimize this first value here, this yellow X. So with this yellow X here, if I just plug in X and I multiply all the matrices together, this top row ends up being a row of X plus 1s. So this row being X plus 1s and all of these others being the same, all we have to do is figure out the best X to have here that makes this top row similar to 4, 2, 3, and 5. So we're trying to get the best X possible to get this close to 4, 2, 3, 5. And all we're doing here is we're taking a least squares. So here, this complicated looking equation is just, as you can see here, 4, 2, 3, and 5. For 4, 2, 3, and 5, we're just going to minus X plus 1 and take the squared error, the squared difference between 4 and X plus 1. And to get this to its lowest possible value, this difference to be the lowest possible value, you actually are taking a derivative, setting it to 0. And basically, you find out that the best X in this current scenario is 2.5. So basically, if 2.5 was here, this update will get this to be close to this. Questions? All right. So basically, we've said that at this point of time, at our first round of gradient descent, 2.5 is the best value here. So if I plug in 2.5, this actually updates to be 3.5. And then the RMSE goes down from 1.75 before. Now it's 1.8 because these numbers are all on average closer to these numbers. So this process is going to be repeated over and over again, not just for like, well, I mean, yeah, it's going to be repeated for every value in here and every value in here. And basically changing different values are going to update different rows or different columns at a time. So every time a single value is updated in any one of these, an entire row or an entire column changes by the same amount. And so that is why you're maintaining the relationships within users and also within items. And that's like before I had the word parallelizable. That's the property of this recreated utility matrix. So it might not look exactly the same as this at the end, but you can maintain that, all right, it's still maintaining patterns within items and within users. This next slide just shows all of this was done. Honestly, what these values are now irrelevant. What's relevant now is these updated values. This I actually plugged into the actual SVD algorithm that got all of these numbers. And our final RMSE is 1.15. So in total, we went down like a full 0.6. So yeah, this is not going to match this exactly just because we want to maintain the item and user relationships. But yeah, basically gradient descent was done over and over again. I will say it will go over these not just once, but many, many times, because once you've updated everything once through, 2.5 is likely not going to be the best value again. So it's just going to do that over and over again until you get to a low enough RMSE. And this process should end up converging or plateauing off. And that's the algorithm. Questions? Cool. All right. Well, this is the last slide. So basically, we've talked about non-personalized, we talked about content-based, and then out of collaborative filtering, we talked about the user-to-user and item-to-item algorithms. And then finally, we have our SVD algorithm, which was this. If there are no questions on the algorithm, I want to dive into the code just to show some really quick things about implementation. Recommendation engines and what this SVD algorithm is, it's within this library called Surprise. It's actually built on scikit-learn, so it has a lot of scikit-learn functionalities, but slight differences. So I do want to point out these differences just in case you run into any issues. So we're going to do this 2 times, once with a built-in data set, once with my own data set. So things that we're importing are usual, but also we have these data set and reader objects. This is the thing that I want to point out in a little bit, because these algorithms take in your data in a different way. You can't just plug in your regular data frames. Why that is, I'm not sure either. So let's run this real quick. If you remember, in scikit-learn, there were a bunch of built-in data sets. Same thing here. This is a movies data set with 100,000 different ratings. And the annoying thing about this is that you actually cannot inspect the data. But with this data, we can still build a model. You can just assume, well, I'll show you the data. I'll show you a data set later, but it's in the same format. Because it's a scikit-based model or library, sorry, same processes. Instantiate the model, fit it to your train set, and test it on your test set. Because you do a train test split on your existing ratings, even though you're filling in the utility matrix, you do have some ratings that you can validate. So you can get an overall accuracy. So yeah, why don't we run this? Takes a little bit to train because it's doing all of that gradient descent process, and your overall accuracy is, oh sorry, not accuracy, but your overall root mean squared error between your test set and the predictions on your test set, 0.938. And then finally, this is just because this data set is set up that way. But if you feed it in like a user ID and an item ID, you actually can get any prediction. So just because this data set has their strings as numbers, their numbers as strings, for like user number 180 and item 304, we don't know what it is right now, but the estimated rating was 3.35. And if we just change these around, you see that item 306, estimated rating 4.25. User number 18 has this estimated rating. So this is just like a quick rundown of all the scikit functionality that we have here. Next, we're going to apply it to an actual data set. So this is actually my capstone project. I built a Yelp recommendation system, basically recommending like restaurants and businesses off of Yelp using this algorithm. I will say the capstone 2 years ago, very, very different from what it is now. It is a lot harder now. It should be a lot harder now. But basically, this is what the data frame should look like. As I mentioned before, storing everything in that matrix method, very, very inefficient, and Surprise knows that. So all of these are user IDs, business IDs, number of stars. This is a data set that we're going to plug into Surprise. This is just some really, really quick EDA. You all know this, so I'm not going to go through it right now because I see that we're low on time. Now, this is the new thing that I wanted to point out. You have 2 objects that you're going to instantiate here. So first, a reader object. This is where you tell it your scale of ratings, just so it'll never recommend anything above 5 stars or or it won't predict anything to be above 5 stars or below 1 star, just because ratings are bounded. So you need to tell it what the rating scale is. So Yelp 1 to 5, something like, I don't know, Airbnb I think is out of 100. No, that's not true. That's also 5. But yeah, this, you have to tell it what the rating scale is. Next, the data set object. Again, it was kind of annoying that, you know, you can't see the data once you put it in this object, but that's just the way Surprise takes in your data. So here I'm loading in my data from, it has a load from df method, which is pretty neat. I'm calling on my 3 columns, and it has to be in this order. It has to be user ID, item ID. I mean, in this case, it's business ID, but depending on your problem, it'll be a different ID, and whatever the ratings is. And in this case, it's stars. And this is where I also have the reader object. So in this data set instantiation step, I have the data frame and the rating scale. So with this done, I do the same train test split. Again, this is just to show that you cannot really inspect your data, unfortunately. So you have to do your EDA before you do this step. I mean, you should be doing your EDA before anyways. But finally, we're going to fit, you can fit and evaluate your models. So these are some of the hyperparameters that you tune for SVD. First, number of factors. So number of factors is the number of latent features. So in this case, it's just, you know, here n factors would be 2 because I'm using 2 latent features. So again, higher number of features means you get more like granularity in how you represent your users or your items. Downside is it will take quite a bit longer. But you can also do like grid search and everything. It's all built into Surprise. I think that their documentation is actually really well set up. So n factors, this is another one, number of epochs. So number of epochs is just a number of times it goes through all of these numbers. So if I were to like, you know, update each of these 8 numbers and these 8 numbers, that counts as 1 epoch. So 20 epochs means that it's going to keep updating this. It's going to go through 20 rounds of figuring out the best values. So you can argue that the more epochs, the better. But again, it'll just take longer. Also, maybe overfitting. Bias equals true. I forget what this is off the top of my head. It probably says it definitely will say in the documentation. This is the learning rate. So how much, basically your rate of your gradient descent learning and how fast it converges. And this is regularization. You can also introduce regularization here. And so this will probably counter the overfitting from your number of epochs. And so with this, we can fit it on our train set, and then we test it on our test set. You can see here that with predictions, and this is just the first 3, I believe the test set was, let's see, if I do test set dot length of test set, 20,000 in our test set. This is just the first 3. Each prediction, let's just look at one first. Each prediction shows you what user, what item it is, what the actual rating was, because it is your test set, and the estimate. So you can see here, not too bad. It's like maybe 0.7 off. And in context, think about, all right, if I'm doing a Yelp recommendation system, is it a big difference if it's 4 or 5 stars? Maybe it is, maybe it isn't. Up to you to decide. So we can look at a few of them. Here, the real rating was 3, estimated 3.235. Real was 4, estimated 4.02. So pretty good. These are like the overall metrics. So an RMSE of 1.29, MAE, mean absolute error of 1.05. So on average, you're about like 1 star off for each recommendation. So here, just to use, I mean, this is just because of this data set. Each user ID and business ID is this convoluted string. We can plug in these values into our .predict. So with this .predict, you can see that for whatever this user is and whatever this item is, the estimated rating will be this. Of course, I don't have this data set here, but you can get the Yelp data set and figure out who the user is and who the item is, and you can make recommendations that make sense. Just really quickly to go through the resources that I have here. Surprise does have sample code where you can get the top N recommended items for a user. It is literally laid out for you, so you're welcome to use that. This is a textbook that I think if you're really interested in recommendation systems, I really like this book. That's how I got to understand all of these algorithms. That's a really good book. It is quite dense, so I wouldn't do it now. I would save that for later. Surprise, this is the library that we use today. This LightFM is a library that actually combines content-based with collaborative filtering. I don't recommend it for this phase 4, this mod 4 project. If you don't have the time, feel free to explore if you want to, but usually that's saved for like a capstone project. I also wrote blogs on this topic just because I like it so much. So feel free to read. I know that the URLs are the same, but this one links to the next one. I just keep forgetting to update the URLs here. But yeah, that's all I have. Any questions? I know we're a little bit over time, but I'll take some questions, if any. Perfect. Well, this is the first of 4 topics that you can do a project on this mod. I won't be hurt if you don't choose this, so don't worry about it at all. So yeah, if you don't have questions on this, Thursday we kick off time series. I know time series is very popular and just because it has a lot of like direct application for like forecasting. So we'll see that on Thursday. Highly recommend going through at least some of section 35, 30. What's the first time series section, basically, because that goes through a lot of like pandas functions for dealing with time series data that I'm not going to go through those during the study group because it's just like learning different methods. So yeah, cool. Well, that's all I have for you all. Final questions before we call it. All right. I will see you all on Thursday then for time series. Have a good evening, everybody. Bye.
Bye.